Hello, I'm Harold McNair.
In this section, we're going to talk about GC detectors, specifically the flame ionization detector, FID, thermal conductivity, TCD, and the electron capture, ECD. We will not discuss the mass spectrometer today, but at a later time. The flame ionization detector is basically a hydrogen flame, very pure hydrogen, typically 30 to 40 milliliters per minute, burns here, supported by a supply of air supplying oxygen. Typically 300 to 400 milliliters of air enters this detector. That is used to support the flame. The flame is ignited by a simple coil right here, and then as organic compounds are carried from the GC column into the detector, they're combusted. They generate small negative and positive particles, and the charged particles are collected by two electrode systems, a positive electrode here, a negative electrode here. People like to think sometimes of collecting electrons. In fact, they're small negative particles, not necessarily electrons. But in any case, this is a very efficient detector where a large current is generated from a very small amount of carrier gas which enters bringing the samples in. Here we have an example of trace impurities in pure heptane. This hexane peak right here represents 100 parts per billion, or 3 times 10 to the minus 11 grams of hexane. Very small amount. Thus the biggest advantage is that for organic compounds, very good sensitivity. If we summarize the flame ionization detector, the minimum detectable quantity is around 10 to the minus 11 grams, or about 50 parts per billion. The type of response is only organic compounds. Organic compounds which can be combusted to carbon dioxide, no fixed gases or water, no inorganic compounds. The linearity, that range over which the peak area is directly proportional to concentration, is excellent. A million-fold range of linearity, thus one of the best detectors for quantitative trace analysis. Stability, excellent. Very little effect of flow rate or temperature changes on the detector response. Upper temperature limit of the detector itself, 400 degrees centigrade, and the carrier gas can be either nitrogen or helium. In summary, a rugged, can withstand flow and temperature changes, destructive. The sample is destroyed. After the flame ionization detector, there is no more sample. It does require 3 ultra-pure gas supplies, hydrogen, air, and the carrier gas, as well as a very good electrometer. One of the most widely used detectors in gas chromatography. The second detector is a thermal conductivity cell. A large metal block is held at a constant temperature, let's say 250 degrees centigrade. Inside the block there are basically 4 filaments. 2 of these filaments are measuring filaments, 2 of those filaments are reference filaments arranged in a Wheatstone bridge. A current is passed through this filament and it is heated, slightly hotter than the block itself. If this block is 200 degrees centigrade and the filament has a current of 300 milliamps, it's somewhere around 235 degrees centigrade. As pure carrier gas flows over the filament comes to temperature equilibrium between the current input and the thermal conductivity loss to the flowing carrier gas. Now, as organic compounds or any compound with a higher molecular weight enters from the GC column, it conducts temperature less well than the pure helium. Therefore, the temperature of the filament increases slightly, less than 1 degree centigrade. It is impossible to measure the difference in temperature of the filament, so we use a Wheatstone bridge. And a Wheatstone bridge simply measures the change in the conductivity of a filament with respect to the temperature of that filament and the block. The minimum detectable quantity is limited somewhat. Here we see pure heptane, 300 milliamps, helium carrier gas, and this small peak here represents about 10 parts per million of normal hexane. Big advantage of TCD, it is universal. It can measure anything except the carrier gas itself, and helium cannot be used to measure hydrogen quantitatively. That's a special problem to be discussed later. If I summarize the response characteristics of the TCD, minimum detectable quantity, about 10 to the minus 9 grams, corresponding to about 10 ppm. Response, all compounds except for hydrogen, which gives a signal, but not a quantitative signal with helium. Linearity is fair, 10 to the fourth. Stability is good. Carrier gas is typically helium, sometimes hydrogen. Temperature limit, 400 degrees centigrade. And in summary, a non-destructive. Thus you could couple or connect another detector after the thermal conductivity. Moderate sensitivity, easy to operate, requires a good temperature and flow control, which are easily available with the modern day instrumentation. The last detector discussed today is the electron capture detector. A radioactive source, today typically nickel-63, emits a very soft beta. Beta is just simply a slow electron. Carrier gas could be helium or nitrogen, typically helium. If helium is used as carrier gas, we introduce an extra supply of nitrogen. Nitrogen has a very low ionization efficiency, thus the beta particle strikes the nitrogen, it liberates at least 2 or more electrons, leaving a plus N2 particle. These electronegative species go to electrode and generate a very high signal. With no sample present, there's a very high standing current, about 10 to the minus 8 amps. However, when sample is present, when those samples contain electronegative molecules, molecules containing fluorine, chlorine, bromine, or polynuclear aromatics or nitro groups, these electronegative molecules capture these electrons, decreasing the signal. Thus, when sample is present, the free electrons are captured. Rather than going to the electrode system, they're captured, and therefore there's a loss in standing current, which is measured. This is the only detector which generates a negative signal, because that might confuse you. As soon as we go to electron capture mode, we invert the normal chromatogram, and you see the loss in signal as positive peaks, which you're quite familiar with. Advantage of ECD is great sensitivity, great selectivity. Here's a blank of a solvent used earlier, benzene, and then a spike sample containing 0.2 picograms of lindane, a very common pesticide, which represents 200 femtograms. That's over 200 parts per trillion of that particular sample. 0.1 picogram of heptachlor, 0.1 picogram of aldrin. Thus, in summary of the electron capture, the minimum detectable quantity varies depending on the number and the type of the electronegative atoms, 10 to the minus 9 down to 10 to the minus 12 grams. Response, very selective. It's difficult to say, but of all the compounds we deal with in gas chromatography, only a small percentage, maybe 1 to 2%, give a good signal by electron capture. Linearity is only fair, 10 to the third, 10 to the fourth. Stability is only fair. But in summary, the detector is easily contaminated because of extreme sensitivity to traces of water and oxygen, non-destructive, concentration dependent, but very sensitive and very selective, and widely used for pesticide analysis. Earlier estimates by FDA showed they felt a few years ago that daily there are more than 30,000 samples of pesticides in food done throughout the world on a regular basis. Today there's probably at least 35, 40, maybe 50,000 samples of pesticide in food done routinely on a daily basis by electron capture. If we summarize all of the common detectors employed, we have here the capability to measure micrograms, nanograms, and picograms. The thermal conductivity is limited in sensitivity. Still widely used because it's cheap, it's simple, and nanograms means about 10 to 50 parts per million. Flame ionization is more sensitive, and we see a very nice detection limit down here approaching about 100 ppb. Electron capture, a more limited range in terms of quantity of knowledge, but very good sensitivity, less than picograms. And of course, several other detectors shown schematically, but if we compare TCD, FID, and electron capture with a mass spectrometer, in the scanning mode, where all the ions are recorded, we have here sub-microgram all the way down to sub-nanogram level in the scanning mode. But by going to single ion or selected ion monitoring, we have sensitivity which is better than electron capture. In the scanning mode, I compare that equivalent to flame ionization, and the selected ion monitoring comparable to the ECD. Thus, we have a range of very good, sometimes very selective, oftentimes very sensitive detectors.